To fully characterize polyolefin resins, it is ideal to use a bivariate distribution analysis, which gives molar mass distribution, short-chain branching distribution, and their interdependence. However, this technique demands significant analysis time. For practical purposes, the focus is usually on obtaining the distribution of molar mass and the distribution of short-chain branching, as they are considered the most critical parameters in the microstructure. This video centers on explaining short-chain branching distribution and how to measure it. To understand short-chain branching distribution, we will look at its significance when present in polyethylene and polypropylene copolymers. Within the polyethylene family, we examine SCBD by comparing resins produced with single-site catalysts to those produced with multi-site catalysts, highlighting one of the most important industrial resins in the market: linear low-density polyethylene, or LLDPE copolymers. The most important classifications within the polypropylene family are the EP random copolymers and high-impact PP copolymers. Polyolefins have the simplest chemistry of all synthetic polymers, made of just carbon and hydrogen atoms. However, they can have complex microstructures with the incorporation of comonomers and the use of multiple reactors or different catalysts. The major feature is the incorporation of short-chain branches, which largely influence crystallinity and can be present in different short-chain branching distributions, or SCBD, significantly impacting product performance. The microstructure of a polyethylene homopolymer is the sequence of CH2 groups in linear chains and can be unequivocally defined by the molar mass distribution. To extend the range of polyethylene applications, alpha-olefin comonomers are incorporated in the reaction process, resulting in the presence of short-chain branches. Industrial polyethylene copolymers incorporate different levels of short-chain branches, leading to a broad range of densities and crystallinity. When copolymers are produced in a single-site catalyst, a uniform distribution of branches along all the polymer chains is obtained, resulting in a narrow short-chain branching distribution. These copolymers are then unequivocally defined by the average number of branches per unit length, together with a narrow molar mass distribution. The microstructure of these copolymers, in terms of short-chain branches, can be schematically represented, as shown below, with fractions of different molar sizes. All have similar branch content per unit length, and the corresponding narrow short-chain branching distribution in this example. However, most commercial PE copolymers are produced with multiple site catalysts MSC and/or in a dual reactor process, and are known as linear low-density polyethylenes, or LLDPE. It is with these resins that the importance of defining the distribution of short-chain branches was first demanded, because it can result in bimodal and sometimes trimodal SCBD. The microstructure of these copolymers in terms of short-chain branches is represented below with fractions of similar branch content per unit length, with a corresponding bimodal distribution in this example. Interestingly, the short-chain branching distribution of Ziegler-Natta LLDPE resins shows the dependence of comonomer incorporation or branch content with the molecule's chain length. Techniques to measure the short-chain branching distribution demand a separation process of the polymer solution according to crystallizability, which, in the case of PE copolymers, is influenced by the irregularities produced by the branches in the molecule. A linear dependence exists between crystallization or dissolution temperatures and the number of short-chain branches, and this is usually expressed as the number of methyls per 1,000 carbons or as the percentage of comonomer incorporated. Isotactic polypropylene is a semicrystalline polymer with a methyl branch every 3 carbons, that is 333 CH3 over 1000 C. Polypropylene applications can be extended with copolymers by the incorporation of ethylene in the linear chain, reducing the number of methyl branches, which in this case results in lower chain regularity and crystallinity. The number of methyls per 1,000 carbons follows an opposite relationship with crystallization and dissolution temperature to that of polyethylene. The degree of isodacticity of the various fractions also influences chain regularity. The overall SCBD distribution provides a valuable microstructure description of these ethylene-propylene copolymers. The short-chain branching distribution, sometimes referred to as the chemical composition distribution, is the most discriminating microstructure feature in industrial polyolefin copolymers. To achieve optimum performance, these copolymers are often produced in dual catalysts and/or multiple reactor processes, resulting in complex polymer architectures. Designed and developed by Polymer Car, your trusted partner with over 30 years of experience in advanced polyolefin characterization instrumentation and world-class analytical services.